oxygen, oxygen, propane, air, acetylene, oxygen, acetylene and the like. A preferred explosive fluid mixture is hydrogen and oxygen in approximately stoichiometric quantities, atomic ratio of HO of 2 to 1. For this mixture, a voltage pulse in the range of from about 30 kV to about 50 kV, and typically about 40 kV, for a duration of 1 microsecond is effective. Atomized or vaporized liquid fuels, such as gasoline, can also be mixed with oxygen or air as an effective mixed fluid. Rather than mixed fluids to generate the sonic pulse on detonation, solid fuels can be used. The solid fuels would be packaged in a manner similar to blank shells, but would be larger and have more energy per package than the usual gun blanks. An electronic squibber or percussive primer is used to detonate the solid fuel. Automatic reloading of the solid fuel shells could be accomplished in a manner that is conventional for guns or cannons to accomplish a desired repetition rate. A most preferred acoustic source is an electrically triggered shock tube. Shock tubes are disclosed in U.S. Pat. No. 3,410,142 to Dieber al. That is incorporated by reference in its entirety herein, with reference to Fig. 4a, the shock tube 72 is tubular with an interior bore centrally running theriathra. A frangible diaphragm 74 separates the shock tube 72 into a high pressure region 76 and a low pressure region 78. When frangible diaphragm 74 is ruptured, the pressure differential between the high pressure region 76 and the low pressure region 7 generates a shock wave that travels the length of the low pressure region 7 and is emitted from the shock tube 72 at output N0 as a sonic pulse. Figs. 4b through 4e illustrate the generation of the sonic pulse. In Fig. 4b, the initial pressure distribution of the shock tube prior to rupture of the frangible diaphragm 74 is 573s illustrated showing the high pressure region 76 and low pressure region 78. Shortly after rupture of the frangible diaphragm 74, a shock wave 82 begins to traverse the low pressure region 78. Trailing the shock wave 82, but traveling at a higher velocity is a rarefaction wave 84, as indicated in Fig. 4e. Adjacent to the output end 80, the rarefaction wave 84 catches up with the shock wave 82, generating a high-energy sonic pulse. Fig. 5 illustrates the incorporation of a shock tube 72 into the acoustic canon of the invention. The shock tube 72 has a high pressure region 76 and low pressure region 78 separated by a frangible diaphragm 74. Prior to actuation, both the high pressure region 76 and low pressure region 78 are at substantially the same pressure. Preferably, prior to actuation, both regions are filled with air at ambient pressure. Frangible diaphragm 74, typically a thin sheet of plastic or other brittle material, is inserted into a notch formed through the housing 86 of shock tube 72 and separates the high pressure region 76 from the low pressure region 78. To actuate the acoustic cannon, the gas pressure in the high pressure region 76 is increased by any suitable means. A preferred means is electric arc heating. A first electrode 88 extends longitudinally through a portion of the high pressure region 76 centered about a longitudinal axis 90 of the shock tube 72. A front end 92 is proximate to the frangible diaphragm 74, but preferably the front end 92 does not contact the frangible diaphragm 74. A rear end 4 extends through a rear wall 6 of the high pressure region 76 terminating in a reservoir 8 containing a high dielectric fluid 100 having a resistivity in excess of about 10 ohm/cm. One suitable dielectric is conventional transformer oils. The oil is for insulation only. Other methods of high voltage insulation are equally suitable. Encasing a substantial portion of the first electrode 88 is a dielectric insulator 102. The dielectric insulator 102 covers an entire mid-portion of the first electrode 88, exposing only a desired small amount of the front end 92 and the rear end 94. Disposed about a portion of the dielectric insulator 102 is a second electrode 104. The second electrode 104 has a front end 106 disposed within the high pressure region 76 and a rear end 108 disposed within the high dielectric fluid 100 of reservoir 8. The dielectric insulator 102 defines a longitudinal length L between the second electrode 104 and the front end 92 that regulates heating of the gas contained within the high pressure region 76. When the shock tube 72 is actuated, an electric spark 110 is emitted and traverses along the surface of the dielectric insulator 102 from the second electrode 104 to the front end 92 of the first electrode 88. Increasing the length L increases the time that the gases are exposed to the electric spark, increasing heating of the gases. As the gases are heated, they expand, generating a pressure differential between the high pressure region 76 and low pressure region 78. Increasing the length of L increases the heating of the gases, increasing the expansion thereof, thereby increasing the pressure differential and intensity of the shock wave ultimately emitted from the shock tube. To actuate the shock tube 72, a power supply 112 charges a capacitor 114. The voltage difference between the first electrode 88 and second electrode 104 must exceed the breakdown voltage of the gas contained within the high pressure region 76. For air, a voltage differential of in excess of 100 kV, and preferably on the order of 150 kV 1525 35 40 45 50 55 60 65 6 is utilized. A timing mechanism, not shown, actuates all shock tubes 72 of the acoustic cannon at substantially the same time by electronically closing a switch 116, thereby completing the circuit. Preferably the length L is from about 6 inches to about 36 inches. The spark will traverse a distance in excess of 1 foot in less than 2 microseconds. After each burst of the shock tube, the frangible diaphragm 74 must be replaced. The pulse repetition rate is from about 0.1 to about 5 seconds and preferably from about 0.5 to about 2 seconds. Rapid replacement of the frangible diaphragm is achieved by mechanical means. An advantage with the electric heated shock tube of the invention is that the frangible diaphragm 74 may be omitted. The gas in the high pressure region 76 is heated faster than the pressure can be relieved. The result is a pressured region that expands as a shock wave from the end of the barrel. The frequency content of the sonic pulses is controlled by the barrel length. The output of the pulsed acoustic source is a single pulse that has Fourier components that range over a range of frequencies. The principal, a dominant, frequency will primarily be dependent on the duration of the high-pressure portion of the pulse, that can be controlled to a first order by the energy in the individual shock sources and by the barrel length, as illustrated in Fig. 6. To maintain high directivity, the minimum dominant frequency of the sonic pulses is in excess of about 1 kHz, and preferably in excess of about 2 kHz, as illustrated in Fig. 7. Attenuation increases as the frequency increases such that the maximum dominant frequency of the sonic pulses is preferably less than about 7 kHz, and more preferably, less than about 5 kHz. The sound intensity is selected to provide a desired effect to the biological target, dependent on the application. While the effect of sound is subjective and dependent on an individual's physiology, the Table 1 guidelines are illustrative. Table 1. Effect sonic intensity shockwave pressure threshold of pain 145 decibels eardrum rupture 185 decibels 5-6 psi pulmonary injury 200 decibels 30 psi lethality 220 decibels 100 psi as graphically illustrated in Fig. 8. A sonic generator having a mass equivalent to the total charge mass equivalency of trinitrotoluene (TNT) is capable of producing a shock pulse effective to cause disorientation and debilitation, without permanent injury, over distances of from less than 10 meters to in excess of 100 meters. The Fig. 8 distances were computed based on a single sonic source and do not include the N factor that is obtained using multiple sources. As such, Fig. 8 illustrates the minimum overpressure values at a given range for different values of the source strength energy. Incorporation of the n-degree factor for multiple sources substantially increases the effective range for a given overpressure level. It is anticipated that the acoustic cannon of the invention will weigh less than 50 kilograms and occupy a net volume of about 1 cubic meter, compatible with current light-in-fan tri-vehicles. The discrete nature of the individual pulses comprising the acoustic radiation field essentially eliminates the Pres. 5,973,999 7 ENCE of high-amplitude side lobes, but there will also be no null positions. Off-axis locations will experience peak pressures comparable to those characteristic of the peaks for individual sources at the same distance, but possibly for somewhat longer duration. Consequently, ear protection for the operators is recommended. The advantage of the acoustic cannon of the invention is illustrated by the example that follows. Example: 4 acoustic tubes, each having an inside diameter of 6 inches and a length of 12 inches, were placed at the corners of a 36-inch square. Each tube was charged with a mixture of hydrogen and oxygen in approximate stoichiometric ratio.
Okay. Before you say, my God, she's out of her mind. Talking about all these gases. Okay. Remember, patents are very technical. And if my calculations are correct, and of course this was written in 99, keep that in mind, that slight modifications can be made to this by adding 2 wires that could come together and create a spark. You're still going to need some of the gases. But being that it is very small, and let's say you had a house and you had it upstairs and downstairs, and they usually send in a team of maybe 6 men. The other modification that you would need to have done is that one device will set off the other device. And either you can do this through an application on your phone, which after the first initial shock wave that renders them to their knees, you can get your stuff together, grab your phone,